Hello and welcome to section 11.5 in our gas laws chapter. And today now we're going to be looking at, in this screencast, temperature and pressure. And this is Gay-Lussac'S law that we worked with a little bit in lab. So we're continuing the theme where we have already taken a look at pressure versus volume. And then that was with Boyle's law. And then we looked in Charles' law where we were considering temperature and volume. And now with Gay-Lussac, we're going to put temperature and pressure together. So we're going to be looking at the P and the T as far as the equations are concerned. So in Gay-Lussac's law, the pressure that is exerted by a gas is directly related to the Kelvin temperature. So instead of volume, we're going to put pressure in its place. And remember, in Charles' law, pressure and the amount of gas was going to be constant. Well, in this section, volume and the amount of gas are going to be our constants. So a very similar equation that you're going to be familiar with the setup. Our initial is going to be our P1 divided by our T1, and our change is going to be our P2 divided by our T2. So let's go back and take a look at our containers. So here in our container with our piston, we have a temperature that is at 200 Kelvin, and the pressure is at 1 atmosphere. All right, so we can see that we've got the molecules and they're bouncing around in this picture. So when we increase the temperature, the pressure that's going to be exerted, it means that these molecules are actually going to speed up in the way that they're moving. And when they speed up, it's going to create more pressure. And look at all the pressure points that we see on here. And our pressure is now going to be at 2 atmospheres. So when the temperature increases, the pressure increases. When the temperature decreases, the pressure decreases. Okay, so that's what we're going to be seeing. So remember, we're going to keep the mass, the amount, and the volume of the gas at a constant. We're not going to worry about changing that, so that all we're really going to do is increase or decrease the temperature or increase or decrease the pressure to see the relationship that we have. So let's look at this graph. If we have pressure on this side and temperature on this side, we can see that the direct relationship, as the temperature increases, so does that pressure increase. And it would happen in reverse. If we released the pressure, the temperature would go down, or if we changed the temperature, the pressure would go down. All right, so this is the concept and the visual that you need to keep in mind. Okay, so let's jump right in with this because it's similar to what we've done with past equations. We're just using P1 divided by T1, which equals P2 divided by T2 in our equations. So let's say in our example that we have this sealed can, and the pressure in this sealed can is at 235 kilopascals when it's at room temperature, which is 20 degrees Celsius. So let's say that we warm this can, and we warm the can to 48 degrees Celsius. And we want to know what the new pressure is going to be inside the can. So first, let's put our equation down. So we learned that our equation is P1 divided by T1 equals P2 divided by T2. So we're looking for the new pressure. So we're looking for P2, the pressure after the change. So that means that we have to get P2 by itself. Much like what we did to get V2 by itself, we're going to do the same thing. So in order to get P2 by itself, we've got to take T2 off the bottom and multiply it by P2. That enables us to eliminate and cross off the T2. Now what we've done to this side of the equation, we have to do to this side of the equation. So we're going to bring T2 up here as well. So our equation for P2 is going to be P2 equals T2 times P1 divided by T1. The next thing is we're going to list what we know, and always get into the habit of listing what you know. So the pressure one, the initial pressure, is going to be 235 kilopascals. The initial temperature is going to be 20 degrees Celsius. We know we have to change that to Kelvin because all of these problems, we want the results to be in Kelvin. So simple, not a problem with this. We're just going to take 20 degrees Celsius and we're going to add it to 273 Kelvin, and that's going to give us 293 Kelvin for our initial temperature. We don't know what our P2 is. This is what we have to solve for. But we do know that our temperature 2 is 48 degrees Celsius. Again, real simple. We've got to change this over into Kelvin. So we're going to put 48 degrees Kelvin plus 207, or 48 degrees Celsius, with 273 degrees Kelvin, and that's going to give us 321 degrees Kelvin. Okay, we have all that we need to know here. So let's put it into our equation. So we're going to put P2 equals, well, we need temperature 2, and our temperature 2 we found out is 321 Kelvin. So we're going to put 321 Kelvin right here to take the place of our T2. Next, looking at our equation, we need P1. Oh, let's look. P1 is 235 kilopascals. So we're going to put 235 kilopascals. We're going to multiply that with our 321 degrees Kelvin because that's what we need to do from our equation. Now we need to divide it by the initial temperature. And our initial temperature, when we go back and look at our given, is 293 Kelvin. So we're going to put that on the bottom. Now we can cancel out our kelvins. That's going to leave us with kilopascals. So let's enter this into our calculators, and we're going to put 321 times 235, and then we're going to divide that by 293. So what we should be seeing is our P2 is going to be equal to 257.46 kilopascals. All right. Not too bad, right? This is something that you can do very easily. Let's try some more. Okay, so here's our next problem, and notice it's blank, so guess what that means? You got it. This one you're going to do on your own, and you're going to turn it in so that I can see how you did. A gas has a pressure at 2.0 atmospheres at 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius? Keeping in mind that the volume and the amount of gas is going to be constant. So here's what I want you to do. I want you to show me your equation and show me how you're going to change that equation so that you can solve it. I want you to list the given, what you know, and then I want you to put it into the equation, and then I want you to explain your answer in terms of temperature and pressure. Did the temperature go up and increase the pressure? Did the temperature go down or decrease the pressure? Or did you see something differently? All right, so that's what you're going to put for this answer. Good luck. How did you do on that last problem? I'm sure you did well because you're just picking this up really easy. You're probably thinking, this is a breeze, Mrs. Saunders. Okay, so let's try another one. In this problem, again, notice the blank space. So this is going to be another one that you're going to be turning in. You have a gas that has a pressure of 645 millimeters of mercury, and it's at 128 degrees Celsius. And we need to know what is the temperature in Celsius if the pressure increases to 150 atmospheres. Remember, the temperatures are going to be, the volume is going to remain constant and the amount's going to remain constant. So again, show me that equation. Show me the original one and how that you're going to change that original equation. I want to know what your givens are. I want you to, don't forget, you have to first convert into Kelvin, and then you're going to have to take it out of Kelvin because the question is going to ask for Celsius. New little twist to this. So I want you to show me your problem, and then I want you to show me how you would get it back to Celsius. Okay? Good luck. You've got this.